Okay, this is a review of Quiz 2 in AP Chem, and let me close this little window here. So, question number one. So we'll just look at question number one. First thing you had to do was rank these acids from the strongest weak acid, from the weakest to the strongest. All right, so we've got pKa. pKa is the negative log of the Ka. So pKa is going to have the same uh, relationship as pH. The lower the pKa, the stronger the acid, okay? The bigger the Ka, all right? So of these, the lowest one is hydrofluoric acid. Therefore, it is our strongest acid. The weakest acid is going to have the largest pKa. Therefore, the weakest is hydrocyanic, okay? Followed next by benzoic, and then by nitrous, and then finally by hydrofluoric. Hydrofluoric is the strongest of the group. It has a pKa. It has the lowest pKa. Okay, so there we go. So pKa is just a very efficient way of expressing Ka. Just like pH, the lower the pH, the higher the hydrogen ion concentration, the lower the pK, the larger the Ka, the stronger the acid. All right, these are all weak acids. So when we're talking about weak and strong, we're talking about things in relative. All right, write the most complete form of the reaction that shows how this acid acts as an acid. We'll do all three, so all four, excuse me. HNO2 to be most complete. All right, we're going to show the water molecule, and we're going to show that our acid is indeed a proton donor, and therefore the two products are going to be hydronium ion and nitrite ion. All right, got to be able to write those reactions. If we were doing hydrocyanic acid, we'd start out with HCN, reacting with water. Again, very similar pattern. The hydrocyanic acid is going to be the proton donor. Don't be afraid to draw that arrow. Hydronium ion plus cyanide ion. Continue on. We've got hydrofluoric acid, HF, one of the strange ones. Okay, hydrofluoric acid, even though it's a halogen, is a weak acid as opposed to its counterparts in that column, which are all strong acids. We can tell it's a weak acid because of its Ka. So don't be fooled there. So hydrofluoric acid donates a proton to water to form hydronium ion and fluoride ion. And then finally, benzoic acid, an organic acid, C7H6O2, reacts with water to form hydronium ion and the acetate ion, H6O2 with a minus charge. All right, notice the pattern in all these reactions. Okay. Again, we could have shorthanded any one of these reactions as just representing the acid as HA, H plus A minus. But if we want to show things as completely as possible, particularly if we want to be able to identify acids and conjugate bases, this is the way to do it. All right. Second question, identify conjugate acid-base pairs. So for example, if I was doing the nitrous acid, the HNO2 is the acid. Its conjugate base is NO2 minus. Okay, again, conjugates are acids, bases on opposite sides of the reaction that only differ by a hydrogen ion. The acid would be hydronium ion here. The base would be H2O. So in any acid-base reaction by the Bronsted-Lowry definition, we can always identify two acid-base pairs. And so if we go through these real quickly, again, acid, conjugate base. Acid, conjugate base. Acid, conjugate base. Acid, conjugate base. All right, pick another color, go back. Acid, conjugate base. Acid, conjugate base. Acid, conjugate base. Acid, conjugate base. Bingo. All right. So really important to be able to identify those acids and their conjugate bases, because we know there's a relationship. We know that if the acid is weak, the conjugate base will be weak. Okay, this becomes very important. Nice little relationship that says the Ka of a weak acid, the product Ka of the weak acid times the Kb of the weak base is always equal to Kw. So as the strength of one member of that conjugate pair team goes up, the corresponding strength of the other one has to go down. So as we look at these, since hydrofluoric acid is the strongest of the weak acids, its conjugate base, fluoride, F-, is going to be the weakest of the bases. Okay? So, hope that makes sense. On the other hand, hydrocyanic acid is the weakest acid. Its conjugate, Cn-, will be the strongest base. Okay? So, here are the conjugate bases. We'll deal with those in the next problem, but important to understand that relationship. Okay? Relatively strong acid, relatively weak base. Relatively weak acid, relatively strong base. Relatively strong acid, relatively weak base. Relatively strong acid, relatively weak base. Again, it's all summarized mathematically by this lovely little relationship. A Ka times Kb is always equal to Kw. All right, moving on. Write the equilibrium expression constant for the acid ionization. Again, any of these reactions, if I take the first one, the Ka is going to equal the concentration of the hydronium ion times the concentration of the nitrite ion divided by the concentration of the nitrous acid. Okay? Again, we do not include water as part of the equilibrium expression. And the reason for that is water, because it's present in such a large quantity, remains constant in the process. Okay? And so it actually ends up being incorporated into the equilibrium constant. Again, I'm going to write the shorthand general form of that. Ka is going to be H plus NO2 minus divided by HNO2. Bingo. All right, are we good with that? Expression would be identical for either one, any of these reactions. Okay, we would just change the suspects. Okay, got to be able to do that. Do not include H2O. Common mistake. You can almost make a good solid bet that you'll be asked to write an equilibrium expression on the AP Chem exam. Don't blow it. All right. Determine the pH of a 10th molar aqueous solution of your selected acid. Again, we'll keep going with our nitrous acid example. So HNO2 goes to H plus NO2 minus. Again, everything is an aqueous solution. We'll use our shorthand version. Again, ice is nice. Initial concentration is 0.10 molar. Initial concentration of hydrogen ion, we're going to assume is 0. Nitrite ion is 0. Again, that hydrogen ion concentration being 0, we're neglecting the contribution from water, 10 to the minus 7th molar. Again, X is the change. Reaction has to go to the right, minus X. I know you're getting tired of seeing this. At equilibrium, concentration has to be 0.10 minus X. This is going to be X, and this is going to be X. We plug those into the equilibrium expression. X 0.10 molar minus X equals the Ka. The Ka is going to be equal to 10 raised to the, for nitrous acid, pKa was 3.4, so to get the actual Ka, we're going to take 10 and, or raise 10 to the minus 3.40 power. Again, Ka is going to equal 10 raised to the negative pKa. So the same approach you would take for determining the hydrogen ion. If you're given the pH, you'd use to determine the Ka. Okay? Now, simplifying assumption, assume X is small relative to 0.1. Another way to say that is X is much, much, much less smaller than 0.10. Okay, we make that assumption. X is going to be equal to the square root of 0.10 times 10 to the minus 3.40 power, all the square root of that, and X works out to be 6.3 times 10 to the minus third. Notice that our assumption is pretty good. Remember, that's 0.0063. If I round that off to the nearest hundredth, that's going to be 0.01. Going to make about a 10% difference. We're willing to accept that. Okay, so X is equal to this, which is equal to the hydrogen ion concentration. Therefore, the pH of this solution is the negative log of 0.0063, which works out to be 2.20. All right, that makes sense. Relatively, first of all, the pH is less than 7, right? Okay. pH is not quite as low as it would be if it was a strong acid. If it was a strong acid, remember your benchmark, if strong acid, like HCl, the H plus concentration, if we had a 10th molar solution of HCl, H plus would be equal to 10th molar. Strong acids are completely ionized, and therefore the pH for a strong acid with a 10th molar concentration would be 1.00. So as comparison purposes, this is sort of our benchmark. Strong acid, completely ionized. Here is our weak acid, partially ionized. It definitely has an acidic pH, but not as low as what we would get from a strong acid, but still relatively low, which makes sense because this is a relatively strong, weak acid. I hope everything I said there makes sense. Finally, something that seemed to bother people a lot, determine the percent ionization. Percent ionization just is a measure of how many of our original acid molecules, and I'll stick with the nitric or nitrous acid example, how many of those nitrous acid molecules, what percentage are undergoing ionization, okay? Now, keep in mind that this reaction, when we say this reaction is at equilibrium, the HNO2 is ionizing at the same rate that the ions are reforming, okay? But that process is happening, but there's always going to be a constant number of molecules ionized because the forward reaction and reverse reactions have the same rate. So percent ionization is just going to be equal to X. X gives us the measure of how much of the acid ionized, the hydrogen ion concentration, divided by the original concentration. So we'll come along here and say 6.3 times 10 to the minus third molar divided by 0.10 molar. Because it's a percentage, we're going to multiply it by 100%. Okay, and that works out to be 6.3% ionized. To put that in perspective, if we had 1,000 HNO2 molecules floating around in a certain volume of solution, okay, 63 would be ionized, and the other 937 would be unionized. All right, so even though we classified this as a relatively strong weak acid, okay, it's still only a very small fraction or percentage of the molecules are ionized. All right.